Hey, today we're going to go through the beginner's guide to induction heat treat. This is something I've worked a lot in, so we're going to sample it up for you. What is induction heat treating? Induction heat treat is a heat treat method that uses the principle of inducing a current into a part. So what that means is through using electricity to create a magnetic field around a part. It heats up the surface of the metal and changes the structure, making it harder on the surface. As you can see here, you've got a metal coil winding here, and when you put power to two opposite sides in that and let it come through kind of like a resistor on a light bulb, what that does is that creates a magnetic field wrapping around in between and around the outside of those coils. So kind of on the surface of the part, it kind of looks like this. Everything's bouncing together, and it makes the particles move around so fast, it causes the metal to heat up really quickly, and generate, as it heats up, the longer it heats, the deeper the heat will go into the part. So this is an example of a copper heat treat coil, water cooled, around a part being induction heat treated. As you can see, there's a gap here, and this is where that field of magnetic current is running. It's running all around this copper coil. So you get the part inside and it spins, and we'll show you an example of that here shortly. And what it does is it causes all these particles on the outside to start heating up really fast. So why use induction hardening? Speed of heat treating a part, it takes seconds, not minutes. Unless, for bigger parts you can actually do, 60 seconds, whatever, for something that could take 2 to 3 hours in a batch oven or a furnace. The quality of the parts you can control better. The versatility of induction hardening can go from anything from gears and sprockets to camshafts to through hardening to just running stuff through forging machines to heat up billets. So there's a lot of versatility with an induction hardener. And the cost of operation. You're not spending all that time to take the metal from in batches of say 50 in a few hours to hold it at a temperature for a certain amount of time. Now you can take it in seconds up to that temperature, and you only have to hold it for a matter of seconds at that temperature, then quench it, cool it down, and it's on to the next process. So here you can see they have a part inside copper coil. This is a handheld machine made by GH Induction. It's just a quick demonstration they put together, and I like to thank them for putting this on YouTube. But as you can see, they just shove a rod in there. Look at how fast this thing heats up to glowing red. Now, since this is a water-cooled copper coil, they can reach out there, touch it, nobody gets burned. Now, for single shot heat treat, what they call single shot is you put the part in, the whole part gets heated at one time, not just not a scanning operation. So scanning operation is heating as the parts moving or as the coils are moving. So this is an example of a single shot. I'm actually going to skip forward a little bit on it to try to save some time here. I believe it's right around here. You can actually see this heat up the part as it's rotating. That helps induce the current evenly around the part, and you can kind of see it's heating up any sharp corners and stuff a little faster. Then they spray it down with quench, and that holds that K-step. That keeps it from getting too soft and not holding a good Rockwell on the outside of the part. So then somebody would obviously take that out, and we want to thank Ambrell for that video. Now this video is one that I took myself. It's of a scanning process, and if you watch it here, you can actually see this will heat up and kind of preheat, burn some of that quench off there for where it was pre-rinsed. Now it's going to heat this part, and it's going to scan the heat all the way up to the top of the part, and it's going to quench everything underneath. That quench is springed out in an angle so it doesn't affect the heat pattern, and that allows you to heat a tall part, bigger part with a smaller coil and do more processes and have more variance without having to add a whole lot of different materials to the coil itself. You can see how right now it's cooking about 1400 degrees Fahrenheit, around 950 degrees Celsius. That's the Curie temperature and the crossover point for an S53 steel. So this is a sample of a part off that machine that you just seen. As you can see where it was heating, you can actually see where from the outside in it was heated all the way into this area, but the actual true effective hardened area is where this transition comes from, and then it kind of feathers out into the softer material. So you only measure in so far on this. So the reason we do use induction hardening is mostly for a surface K-step and the controllability throughout the process. They're also used with oven applications due to its ability to heat up quickly, and instead of batch furnaces where they use a lot of gas and have to wait so long. So heat treat quality control. We have testing. We test with the micro Vickers machine, and now what that does is that presses little diamond indentions that are measured after the machine's calibrated. As you can see here, as the diamonds get bigger, that's the softer the material goes. On a part similar to the one we just seen in the scanning operation, you can see an effective case depth they needed to 150 thousandths to 200 thousandths of an inch. And a total case depth of 250 thousandths to 300 thousandths. They keep a tight tolerance with induction hardening, and it's awesome the way they can do that and the way we use these things to do that. So this is an example of something that wasn't hardened correctly. As you can see, it broke. It was either not, it was either cracked, from overheating the material, or there's a possibility that they didn't heat treat it enough. But either way, without proper heat treatment and quality in heat treat, you end up cracking parts and failures in the field. You can see here kind of a different views of a case depth and different etching processes. It's kind of hard to see in this slide, but so the versatility of induction hardening, you have your scanners, your single shots, the different shapes of parts you can heat with these, the different machines you can throw them in. Machines can also be fitted to be quick changed. So like this here, the coil bolts on, so you can actually put a different coil on in a matter of minutes. Takes a little longer to line them up, but depending on your air gaps, you can do it a whole lot faster. The types of induction coils, as we talked, is a single shot. These are fluxural intensifiers, and I'll explain those in a minute. And then we have the scanning coils, where it's heating as it's moving. Fluxural intensifiers, what they do is they take that copper coil with that magnetic field, and they draw that magnetic field in around that copper coil and push heat down into the part so you can focus it more. You can see how much heat's going into the part here versus how much going in after you add an intensifier. So on a coil that goes inside a part, you put all this intensifier material on the inside of the coil, and it pushes the field out towards the outside, as it's shown here. This is your part, this is your coil. This is without intensifier material, this is with it. It's pushing everything out. Here's another one where the coil's on the inside. Again, we're pushing the heat out. Here's one with the intensifier on the outside, and it's heating that groove right there. And they want a little bit of heat here and on here, but they want to focus it right in that groove. So they put that in there, and it's pulling all that magnetic field in and driving that heat into that part. Operational costs to consider: induction heat treat, power, spray, integral quench, one machine with multiple stations, furnace heating. You have power to bring the equipment to temperature, gas necessary to run temperature, and parts throughput. Thank you for your time, and I'd like to thank these folks for allowing me to use their information and videos that I was able to pull offline.